In this demonstration, I'd like to talk about the ventricular system. And before we talk about the ventricular system in the adult brain, I want to talk a little bit about how it gets to where it is. So your brain and your spinal cord, your whole CNS, start out as a flat plate. That flat plate rolls up into a tube. The hole in the middle of that tube remains throughout development and into the adult brain and spinal cord, and we call it the ventricular system. In the spinal cord, it's simple because the spinal cord is kind of like just a long band of cells, a long column, and then the tube is in the middle, and we call it the central canal. In the brain, it gets more complicated because the brain, as you can see, is, pretty busy place, and it's curved. You can see from the corpus callosum, that it is curved and that the cortex is curved. This results in the curvature of the ventricles. Okay? You'll also note that you have two, one on each side. This is the result of your brain when it develops. Let me grab this. It develops into two hemispheres because it starts kind of as a tube, and then the middle of the tube gets pinched and gets anchored. And then the resulting pieces grow like two giant bubbles. And those two giant bubbles turn into, well, these don't match, but here, this one's closer. They turn into your two hemispheres. So you have two cortical bubbles, which make your two cerebral hemispheres. And since you have two bubbles, you have two ventricles, one on each side. So the lateral ventricle is the main ventricle that you're seeing here in this cast. So this is kind of a negative. This is when we pump some plastic into the brain and then peel the brain away, we're left with this cast of the hole in the middle. And so let me go through this slowly, and then I'll point out in some of the brain specimens where these things are in an actual brain. So this is the lateral ventricle. It has an anterior horn, which is in your frontal lobe. It has a posterior horn, and this is inside your occipital lobe. It has an inferior horn, and this is in your temporal lobe. They all three kind of come together here in an area called the trigone. Looking from the front, you can see it curved down in front into the frontal lobe, and because this is from a real brain, it's not exactly a mirror image because nothing is completely symmetrical. If we look from the side, you can see that both of the lateral ventricles drain into a midline structure called the third ventricle. And so everybody says, well, why does it start with the number 3? Well, nobody could decide which one was 1 and which one was 2, left or right. It's kind of like left and right Twix. You've got a left lateral and a right lateral, and nobody cares which one's 1 or 2. But it still leads to the one in the middle being 3. So the third ventricle's on the midline. The lateral ventricles both drain into the third ventricle. In a brain, it's a hollow structure, but here it's the solid canal here is called the interventricular foramen. You may hear it called the interventricular foramen of Monroe, but we're trying to move beyond eponyms and simply call things what they really are because then they make more sense. So the interventricular foramen drains from the lateral ventricles into the third. The third ventricle then drains into the fourth ventricle via the cerebral aqueduct, which you can kind of see here. And I'll show you these things on real brains. The fourth ventricle then opens up into the subarachnoid space. Now, why are the ventricles so important? The ventricles contain cerebrospinal fluid. And that probably didn't, when I was talking about draining, that probably didn't make any sense until I said cerebrospinal fluid, because that is what is in the ventricles, and that's what's draining from lateral to third and from third to fourth. So cerebrospinal fluid is generated by a structure called the choroid plexus, and I have some examples of that I'll show you. And then cerebrospinal fluid gets out of the ventricular system into the subarachnoid space via three little foramina which exit from the fourth ventricle. And you can't really see them, but you have one on the midline, which is the foramen of Magendie, and two laterally, which are the foramen of Luschka. And I wish we had better names and not eponyms, but that's still what they're called. Okay, so I'm going to set aside the model, and I'm going to show you what the ventricles look like, excuse me, on real brains. So, on this one, sorry. Yes. One thing I need to also point out, on the midline, the two lateral ventricles are separated by the septum pellucidum. In this specimen, you can see part of that septum pellucidum here, and I'll show you on some of the other brains where it is in a horizontal and in a coronal section. So if you remove this septum pellucidum, then you can see deeper into the lateral ventricle. And you can just kind of see a window here. And deep in here is the lateral ventricle. Okay? Let's see. Yes, on this brain, we've dissected away some of the other structures. We've dissected away the brainstem and the cerebellum, and you can see a lot more of the extent of the lateral ventricle going deep. And the third ventricle is really interesting because it's a midline structure and its walls are formed by this area called the diencephalon. Once you cut the brain, you kind of lose the third ventricle. But I can show it to you on a coronal section. In a coronal section, just an aside, these brains you'll notice all have tags and little strings. It's because we're very serious about keeping track of all of our anatomical specimens because they are real brains from real people and we really need to keep track of them, so we give them all the label. Here is the third ventricle. So when you cut it, you can see when you cut down the midline, you can see that the lateral ventricles are off to the side. Here's that septum pellucidum I was talking about in the middle that separates the two. And then here's the third ventricle. And it's smack on the midline, so when you cut through it, you kind of lose it. So we talked about the fact that you have an anterior horn, a posterior horn, and an inferior horn. And I want to show you how those look in other pieces of the brain. Okay, this is an anterior section of the brain. So this is your frontal lobes right here. And the reason I know that is because I've got the leftovers of my olfactory, and I have this little gyrus under here called the gyrus rectus, so it's really straight. So if I flip it over, so you can see on the inside, here's that anterior horn of the lateral ventricle. You can see it dead ending here in the frontal lobe. And again, septum pellucidum. And this is what the corpus callosum looks like in cross-section. You've seen it going this way in a sagittal brain, and this is it in a cross-section. Okay? Towards the middle of the brain, this is more anterior, so it's a little bit more. This is an anterior section of the brain. If you were looking at the sagittal, this section is taken at about here, because I can just see the frontal pole here and here. So this is the front, and here's our lateral ventricle again, septum pellucidum, going just a little bit farther back because this is a thick section. We can see the lateral, the septum pellucidum, and the third ventricle, and we can see that inferior horn, which is just here. So that inferior horn that goes down into the temporal lobe, this one. So we've got the lateral, and now we've got just a little bit of this inferior horn down here in the temporal lobe. So that's right there. So lateral, third, and then inferior horn of the lateral. This is kind of still anterior hornish area. Once we get all the way to the back of the brain, into the occipital lobe, we can see the posterior horn. And that's this part here in the posterior lobe. Now, the brain, because it's curved, you have to kind of close your eyes and use your 3D thinking cap and think about how things are curving and what you might see if you cut in different planes. So if we cut the brain straight through the middle, then we can see a sagittal part of the brain. It's called a mid-sagittal cut, and we can see the corpus callosum and a window into the lateral ventricles. When we cut the brain from front to back, it's called a coronal section, like a crown over your head. So that is when we get this view of the two lateral ventricles, and we see other structures that we'll talk about in later demos. If we cut the brain horizontally, we're cutting this way through the ventricle system, and because it's a curve, we'll see the different ventricles in two different places. And that's what we see in this section. This is a horizontal section of the brain. This is the front, this is the back, and here again is that anterior horn of the lateral ventricle. This area is the third ventricle, and here is the posterior horn of the lateral ventricle. Now, we talked about the fact that the lateral ventricles are where your cerebrospinal fluid is made. It's made by this funny-looking little epithelial material called the choroid plexus. You can see it here. I think you can see it. Nope. You can see a little bit of it here, going back this way. And I think those are my best examples. So here and here. This choroid plexus actually does exist in all of the ventricles. And it creates cerebrospinal fluid, and cerebrospinal fluid is an ultrafiltrate of plasma. So it's kind of like plasma, but it has different ion concentrations, and it's what we measure when we suspect a brain infection. They will measure the cerebrospinal fluid and look at it to see that there's any kind of inflammatory response, like white blood cells. If there's white blood cells in your CSF, you are one sick puppy. So anyway, this is the choroid plexus, and it exists in all of the ventricles, and it makes cerebrospinal fluid. Cerebrospinal fluid gets out, again, through those three foramina in the fourth ventricle, the two laterals of Luschka and the medial of Magendie, and then it floats out in the subarachnoid space. And I can't really demonstrate the subarachnoid space. I'll have another demonstration that'll show you a little bit more of the meninges. But the bottom line is, this is the arachnoid. And in life, it's suspended. It looks more like a sponge than a flat layer. And it's full of cerebrospinal fluid. Cerebrospinal fluid is made at a constant rate by the choroid plexus and absorbed by these little kind of cauliflower-looking things on the top called arachnoid granulations. And I'll have some better pictures of these and some diagrams in the lecture that you'll see. But the arachnoid granulations then absorb the cerebrospinal fluid. So there's constant production, constant absorption, and the CSF quite literally floats your brain in your skull. If it didn't, then your brainstem and the base of your brain would collapse onto the base of your skull and squish the blood vessels that are coming in, squish your cranial nerves, and it would be bad. It would be very bad. So cerebrospinal fluid is created by the choroid plexus, absorbed by the arachnoid granulations, and floats your brain and keeps everything from being squished. Lateral ventricles, excuse me, let me move this. So again, lateral ventricles, you have two, a left and a right. Third ventricle, cerebral aqueduct, fourth ventricle. Oh, yes, that reminds me. One of these specimens has a very good, yes, this one, has a very good cerebral aqueduct and fourth ventricle. On the sagittal brain, you can see, again, the lateral ventricle and the interventricular foramen right here. And the third ventricle, which is kind of lost because, again, it's a midline structure and it's very thin, and when we cut it, we lose it. This tiny little gap here, this tiny little canal, is the cerebral aqueduct. It leads then into the fourth ventricle, which is right underneath your cerebellum. Okay, so lateral ventricles off to the, deep to this. Third ventricle, interventricular foramen, cerebral aqueduct, fourth ventricle, and then it goes out from little foramina in here to the subarachnoid space. And that concludes our demonstration of the ventricular system.